I was asked to speak about a particular topic on Sudoku, but I'm going to talk generally, that is what I'm generally going to talk about. We'll talk about other aspects of Sudoku as well, especially if whatever you're interested in. Sudoku started, by way of history, it was supposedly invented in 1979 in America, and it was called Number Place. And then it found its way to Japan, and it was published in Japanese puzzle books under the name of Number Place again. And then a particular Japanese publisher just changed the name and called it Sudoku. And then it was exported by a retired judge, exported back to the UK and under the name Sudoku. And then in about 2004, 2005, and it just took off. There was a craze around that time, 2004, 2005. Took off in Europe and the United States, and it's been popular ever since. I mean, some people thought it would just be a fad and would go away again, but it's actually stayed and it's been in newspapers. There are Sudokus in all the papers, and still going strong. So what is a Sudoku? You probably all know, but here's one I prepared earlier, and it's this is a completed Sudoku grid. So I'll just show you. So this is a completed one, which means that every row has the numbers 1 to 9. Every column has the numbers 1 to 9 exactly once. Oh, come on in. And every box, and the boxes, which are these 3 by 3 boxes here, they all have to have the numbers 1 to 9 as well. So the rows have the numbers 1 to 9, the columns have the numbers 1 to 9, and the boxes have the numbers 1 to 9. And anything like that is a completed Sudoku grid. And the puzzle, a Sudoku puzzle, is something like this, which has some of the numbers missing. So it's the same kind of thing, but some of the numbers are missing, and what you have to do is fill in the blanks. So to give you the mindset for this talk, what I want you to imagine is, imagine you are the puzzle creator. So imagine you were trying to make a puzzle for somebody else, right? So for your best friend, you want to make a really hard one. And you're given this. So how would you make a puzzle? Well, how would you make a puzzle? We can come back to this question later maybe if people are interested in. But I'll tell you one way to make a puzzle. One way to make a puzzle is you start with that. You start with the completed thing, and you delete some of the numbers. Just remove some of those numbers. And what you're going to have then is something like this. Okay, so you're going to have a puzzle. Now, you need to be careful though. And this is the interesting thing. Why do you need to be careful? You need to be careful because one of the rules of Sudoku is that the puzzle should only have one solution. It should have exactly one solution. There's one and only one answer. And the answer to that puzzle is that, and that is the only answer. And that's one of the very basic rules of Sudoku. So if you're not careful, you might create a puzzle that had more than one solution. Obviously, it's going to have, if you start with that and you start deleting numbers, you say, yeah, well, this is what I'm left with, definitely has this as an answer. Definitely this as a solution. But you might have more than one solution. How can that happen? So what I want to show you how that might happen. And what I'm going to do is, I've got my colored marker here, and I'm going to color in 4 of these particular squares here. I'm going to color in, now these are not just any old 4 squares, but these are carefully chosen. But this one, that 3, that's 7 there, and that 3 there. And so that's 3, so I don't know if everyone can see this, that's 3, 7, and 7, 3. And we can pass this around if necessary. But those 4 are very, very important. Why? If you removed those 4, suppose you just removed those 4 and nothing else. what's going to happen is that you're left with a puzzle which has 77 clues. There are 81 numbers in total, okay, 9 by 9. And you're going to be left with 77, and there are actually 2 solutions. Because the 3 and the 7 could be the way they are in that box, or they could be the other way around. There's 7 here, and 3 here, and 3 here, and 7 here. And the rules of Sudoku would still be fulfilled. You'd still have the numbers 1 to 9 in each box. You'd still have the numbers 1 to 9 in each row. You'd still have the numbers 1 to 9 in each column. So this is as technical as I'm going to get, by the way. I don't know what what my audience is like, but you need to be careful. If you remove those 4 numbers, you're in trouble already. So this answers a question, by the way, what's the maximum number of clues you could have in a puzzle? The maximum number of clues you could have. You could have 77 clues and still have 2 solutions. But if you have 78 clues, you're okay. So you're still going to have only 1 answer. So the question, I got interested in this back around when the craze started. And I started asking, I got interested in this question, what's the fewest number of clues you could have? So this puzzle here actually has 17. It has 17 clues in it. And a lot of people had thought of this question apparently around the world. I Googled and I found lots of discussion. And people said, okay, we found ones with 17. And people tried hard to find ones with 16 and nobody could find one. So the question was out there, is there a Sudoku with 16 clues? Is there a Sudoku puzzle with 16 clues? Which means, as I said, can only have 1 solution. And nobody could find one with 16. So the challenge was there, excuse me, while I partake. Challenge was there to either find one with 16 or show that there is none with 16. It doesn't exist. And there's the problem kind of that I want to mainly talk about today. How would you show something like that? How would you actually show that there are puzzles with 17 clues, we know. How would you show there are none with 16 clues? Well, actually, this is a good, let me go back to something else. Let me go back to solving Sudoku. Let me go back to another topic, which is solving. How do you solve Sudoku? It's not really the point of this talk. It's not going to be about solving, but we do need to talk about it a little bit. How do you solve that? Well, human beings have various different ways of doing it. And if you do Sudoku, you'll have probably figured out your own techniques, your own tricks for what goes where. But what people actually do, especially if they're making Sudoku puzzles, what they do is they write a computer program to, hi, come on in. So they write a computer program to solve a Sudoku. And what the computer program essentially, it's not that clever. What it does is it tries all the possible numbers in all the possible ways, and if it reaches a problem, a contradiction, if it gets 2 ones in the same row or something, it stops and it goes back and it tries again, it tries something else, and it just tries everything in all possible ways. It's actually very fast. Computers can do that very quickly. So you can write a solver program, you can write a computer program to solve Sudokus, and they're very, very fast. So what you would do, so one thing we could do, you can also write solver programs. They will tell you how many solutions there are, and they will give you all the solutions if there's more than 1 solution. If it's not a proper Sudoku, it's got more than 1 solution, it might have 1,000 solutions. And you can write the solver program to give you all the solutions, or just tell you how many there are. So here's one way. I want to know, okay, is there a 16-clue Sudoku? So what would you do? Well, there are only a finite number of Sudokus. Would you all agree with that? If I say there's only a finite number, it's very big, it's a massive number, but it is a finite number. There's only a finite number of those. There's only a finite number of ways you can fill in the numbers 1 to 9 in all the squares, satisfying the rules of Sudoku. So how many ways are there? Well, mathematicians have counted the number of ways you can do that. And it's something like 10 to the power 21. And so that's billion, 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 something, something, something. It's something about 10 to the power 21. It's a very big number, but it is finite. And what you could do is, you could do the following. You could say, for each one of those, I choose 16 clues, 16 of the numbers, in all possible ways. Again, that's a finite number. There's only a certain number of ways to do that. It's big, but there is only a certain number of ways to do that. And you could literally try all possible ways. Now, you wouldn't do this yourself. You wouldn't do this in an evening or even in a year. You would write a computer program to do this. But you'd see, okay, it's finite, so it could, in theory, could be done. So that's one way to check if there is a 16-clue Sudoku or not. We try all possibilities for 16. We run it through our solver program, and the solver program will tell us if there's one with only one solution. And if there is one with only one solution, bingo. And if there isn't only one solution, we've tried every single possibility, so we know there are none. So this is what's called the exhaustive search. It's called an exhaustive search for computer science. So you actually try every single possibility, and in the end, you know if the thing is there or if it isn't there. Okay, so exhaustive search is actually probably the only way to solve this problem. And if you're planning on doing that, which I was, then you need to actually sit down and count how many of these are there, and how many of these are there, the completed grids, and how many ways are there to choose 16 of the numbers. And so how many things do I need to check, and how long does it take me to check each one on the computer? You need to sort of work this thing out. And I worked it out if I just did it stupidly, and I worked out how long it would take the computer, and it would take the computer 300,000 years. So I said, okay, that's not going to work. And that was back in 2005, 2006. So I said, okay, forget about it. And I just left it there.
Surely it would be more satisfying to be able to work out some formula by which you can derive.
Absolutely. It would be infinitely more satisfying to be able to sort of a mathematical proof is what you're saying. Yeah. If we had a mathematical proof that we could just write down, and I could show it to other mathematicians and everything and say, there's a proof, yeah, great. But we actually are nowhere near finding that.
The proof just for the two-dimensional one, and presumably beyond that there must be ones for three-dimensional and four-dimensional and five-dimensional.
Yeah. Nowhere near, even for this one. We're nowhere near it. So what we do have a proof of, and I'll tell you this proof now since you asked. You didn't ask, but I'll pretend you asked. I'll tell you the proof that you need at least 8 clues. So what I'm claiming, what the theorem is that you need at least 17 clues to have one solution. And so I'll show you a proof. It's very easy. I can show it to all of you that you need at least 8 clues. Suppose you started with only 7 clues, right? So imagine there's a puzzle here, and imagine it only had 7 numbers were given. Well, their numbers are 1 to 9. So 2 of the numbers must actually be missing. So you're actually missing the numbers given. Let's say they're 1 up to 7. It doesn't matter what they are. Let's say they're 1 up to 7. And let's say that 8 and 9 are missing. So 8 and 9 are missing. So in the clues. So if you take any solution of that puzzle, the 8s and the 9s in the solution could be switched, and you'd get another solution. Because there's no 8s or 9s in the clues, so the clues aren't telling you anything about where the 8s and 9s go. So the 8s and the 9s could be switched in the solution, and you'd get another solution, so you'd have two solutions. Just like the 7 and the 3 could be switched there, in fact. But I'm only talking about 4 numbers there. In that case, the 8s and the 9s, I would be talking about 18 numbers. There'd be 9 8s and 9 9s. So it'd be 18 numbers, which could be switched, but you'd get two solutions. And that's a proof. That's the kind of proof you're asking me about. That's a proof that 7 clues is not enough. So 7 clues is not enough. You need at least 8 clues to have one solution. Now, going even further than that, going even one step beyond that has not been done yet by anybody. Even proving that you need 9 clues hasn't been done.
So people haven't really managed to get it into the second dimension.
We haven't got a proof that there are 9 clues. Never mind 17. So 17 is the goal, but we can't even show there are 9. So for a theoretical proof, yes, we'd like one, but we're nowhere near finding it. So the next step is we've got to use a computer. We've got to do this exhaustive search, which is going to take us 300,000 years. So what happened for me in 2009, I left that problem. I said, forget about it. That's going to take. It's impossible. And then in 2009, I started to have some ideas for how to cut down that amount of time. And I'll explain to you, broadly speaking, I'll explain to you 2 of those ideas. And that cuts down the amount of computer time you need. And if you can cut down the amount of computer time you need enough, then you can actually do it. Okay. So if I could cut it down from 300,000 years to 1 day, then we could do it, for example. I didn't cut it down to 1 day, but let's suppose I could. Cut it down to 1 day, then you can actually do it. You start your computer running, and tomorrow it's finished, and you know the answer. So how do you actually reduce the computer time from 300,000 years to 1 day or whatever? That's very common in computer science, and we use mathematics. The answer is use mathematics to do that. Actually, there are 2 things you do. You use mathematics and you use clever programming. And so you combine 2 things. You use mathematics and clever programming. So let me tell you about the mathematics. The first thing, remember I said, how many of these are there? Well, how many of these are there? Remember I said there were about 10 to the power. Anyone remember?
21, yeah.
Very good. We're at 21. It's a prize. Give me a t-shirt.
T-shirts, yeah. Yep, first prize. There you go.
Yeah. There are about 10 to the power 21 of those. Now, I can actually cut that down because if that grid has a puzzle like that, suppose I were to take that grid and I were to rotate it. I'll just rotate it like that. I still have a Sudoku. Well, pretend the numbers stayed the right way up. Okay. So the numbers are the right way up. It's a different Sudoku grid, but it's still a Sudoku grid. It's still a valid one. So I could take that puzzle and put the puzzle like that, and it's still a valid puzzle, and the solution of that puzzle would be that one. Okay? So if that grid had a 16-clue Sudoku puzzle, then that grid would have a 16-clue Sudoku puzzle as well. So I don't need to check both of them. I don't need to check that and that. I only need to check one of those. So I've reduced the number of grids by 1. That's great. But there are more things you can do. For example, you could take the first 2 rows.
You can turn it twice.
Yeah, you could turn it twice.
And turn it 3 times.
Yeah, exactly. Yeah. So that's 4. That's 4 gone. Yeah. But that actually divides the number by 4. Yeah.
And then you can shift it.
Yeah.
You can,
Yeah, you could do a mirror image, exactly.
so then that's another
Exactly. That's another, combined with those ones, it's another 8. That's 8.
Move any block of 3 down 1, down
No,
2.
Yes,
Any,
I could move the block of 3 here. I could swap that block of 3 rows with that block of 3 rows.
or the one underneath.
Or the one underneath. Or if I any permutation of those blocks.
Turn down 4 ways as well.
And turn down 4 ways as well, yeah. Any combination. I could switch, the first 2 rows could be switched.
When
With-
the block of 3 columns, if you go
Yes, you could do it in the columns as well, yeah. You could switch that block of 3 columns with that block of 3 columns.
to the third one,
Or with the third one, or any combination.
turn down.
And rotations of those. And you could switch columns 1 and 2. Or columns 4, 5, 6, or columns 7, 8, 9. And rows 1, 2, 3, or 4, 5, 6, or 7, 8, 9. You couldn't swap, by the way, rows 1 and 4
they're in a different square.
because they're in different squares. You're going to destroy the Sudoku property if you do that. So you be a bit careful. But there are all these things you can do, and you can combine them in all with each other. They can be combined, and you end up with about 3 million. So you end up with 3 million operations that you can do. And all of those operations will preserve the property of having a 16-clue puzzle. If any one of those grids has a 16-clue puzzle, then all of the other 3 million will have a 16-clue puzzle as well. So I only need to check one. So what we can do is we can take all these grids and put them into groups. We can group them all together into these bunches. And in each of these bunches, we only need to check one in all of those bunches. So that really reduces the number of these things that we need to check. So that's actually using mathematics. There's actually, you can count how many there are. It's a branch of mathematics called group theory. And you can count exactly how many there are. And there's something like 10 to the power 9 that you need to check. So we've gone from 10 to the power of 21 to 10 to the power 9. Big improvement.
So you've gone from your 300,000 years to what at that point?
I've gone from 300,000 years to, I can't actually remember. Yeah, I can't actually remember.
It cuts it down loads.
But it cuts it down a lot.
Yeah.
But it's still too big.
Too big.
But it's still too big.
Well, it's 3 by 10 to the 5, 12 by 10 to the 12, which in years, 3 by 10 to the 9 divided by 10 to 12 in days. There's none of it less than a solid day's computing.
No, it's more. I may have
You may have lost a couple of
I may have lost some powers of 10 there.
one or two,
But-
one or two orders of magnitude,
Yes, I may have lost a bit. But
but lots.
if you work it out, it's still too big. Still too big.
Yeah.
So we've cut it down a lot, but it's still too big. So we need to do more. We need to do more stuff. So let me show you. That's the first idea. Let me show you the second idea. Second thing you can do, which go back to these colored, those colored squares, those 4 squares that I colored in. Remember the second thing we're going to do. So the first thing we did was we reduced the number of grids that we need to check. The second thing I'm going to do is different. It's within a particular grid. Remember I said we're going to choose 16 clues in all possible ways and check each one with the solver program. So I'm going to reduce that number. Choosing 16 clues in all possible ways is a huge number of choices. We're talking about 10 to the power 16 or something. I'm going to cut that way down. And I'm going to cut that way down using these configurations like those 4 squares that I've colored in. Because remember I said if you removed all 4 of those, you've got a puzzle with 2 solutions. So it doesn't matter what else you do. You can't remove all 4 of those. One of those 4 has to be a clue in the puzzle. One of those 4 at least has to be a clue. In fact, if you look at that puzzle, 2 of them are clues. The 7 and the 3 are actually both of them are clues. Neither of these ones are clues. But at least one of those has to be a clue. So that really reduces, so that means I can run through all possibilities for 16 clues in all possible ways, but there are only 4 choices for the first clue. Let's say the first clue. It has to be only one of these 4. And you can find more configurations like that in the grid. And that's the idea. You find more configurations like that, and it really cuts down on the number of choices of your 16 that you have to make. And so you combine that idea with the first idea, and it cuts it down to something which, okay, it cuts it down to about 170 years. So we've gone from 300,000 years to 170 years. So it's time for me to stop. I see the food is here. So we've gone from 300,000 years to 170 years, and that's where the last chapter of the story comes in, which is if you had, that's on one computer. Suppose you had 170 computers, and you could run them all at the same time. Then you could divide up the computation into 170 pieces, run them on 170 computers, and you'd be finished in 1 year. And that's actually, it wasn't 170 actually, it was more like 700. But there are computers, supercomputers, which have thousands of processors, so thousands of individual processors. And I got some time on a supercomputer at the Irish Centre for High-End Computing, and I got, well, roughly speaking, I got the 700 processors for a year, and we ran this program, and it finished, and didn't find any.
There's another rule of Sudoku, as well as no duplicate entries, and that's no guessing.
No?
No guessing.
No guessing.
Why don't I put a 6 in there and see what happens? And then that doesn't
Well,
work, so why don't I put a 5?
You're talking about the solving now.
I'm talking about the
Talking
solution.
about the solving of the Sudoku, yeah.
Rather than proving that there are no solutions, it's a different challenge. But is there
It's a different challenge, but there are puzzles. People have actually studied this. There are puzzles that do require guessing. There's,
they'd be sort of regarded in bad odor by people who do this stuff.
it's an interesting discussion point. Maybe we can come back to it after the food. We can come back to the discussion of how, why do human beings like certain ways of solving Sudokus and they don't like other ways of solving Sudokus? So why do we have that?
We don't have 700 processors, each of which has a year.
Well, why? What's wrong with trial and error? Why don't you like it? It's an aesthetic sense. Right? It's a sense of aesthetics. Yeah.
You want to sit there until you've decided that this is the only thing I can do.
Yeah.
Not that,
Yeah. So it's
if it doesn't work, I'll rub it out and try something else.
yeah.
You want to look and look and look and look until you say, but this one has got to be a 5. Yeah. Can't be anything else.
Exactly. You want some nice, clever reasoning process that tells you that must be a 5, and then we feel satisfied.
What a certain Professor Gormley, now no longer with us, described as mere numerical calculation that and he wasn't in favour of it.
Yes, exactly. Exactly. Yeah.
Okay.
So
That's great. Yeah. I mean, what we can do is, guys, I'm going to just put the food around